Hello everyone, welcome to this lecture of this course heat transfer. So we were continuing the last module that is known as the mass transfer. So this is the second lecture of this module, mass transfer. So in the earlier lecture we have studied the concept of this mass transfer and what is the difference in between the heat transfer and mass transfer phenomena. Then three different modes of mass transfer we have discussed in details. So there we have seen that similar to the three different modes of heat transfer like conduction, convection and radiation, there are three different modes of mass transfer also, which are diffusion, convection and mass transfer by phase change. So all those three different modes of mass transfer were discussed in details in the earlier lecture. So today we will be discussing the rate equation in case of the mass transfer. Like in case of the conduction heat transfer, we have seen that the rate equation is known as the Fourier's law of heat conduction. Now in case of this mass transfer, today we will study that equation which is known as the Fick's law of diffusion. So this Fick's law of diffusion we will study today in details, and different formula associated with this Fick's law and some numericals also we will discuss in this lecture. Okay, so let us start this topic. Now before going into details of this Fick's law of diffusion, let us first discuss the concept of the diffusion mass transfer that we have already discussed in the earlier lecture also. So what was this diffusion mass transfer? So we know that the process of mass transfer as a result of species concentration difference in a system or mixture, it is actually known as the mass transfer. And as long as there is the concentration difference in the system or the mixture, then mass transfer will occur, and it will occur from the high concentration to the low concentration in case of the different species. Now we have studied there are three different modes of mass transfer, and the number one is diffusion, next is convection, and the number three is the mass transfer by change of phase. So the diffusion mass transfer concept we have discussed in details. So it was actually the transport of water on a macroscopic level as a result of diffusion from a region of high concentration to low concentration region in a system or the mixture of liquid or gases. So this is the phenomena of the molecular diffusion. So what happens there? Due to the concentration difference, that is from a region of high concentration to the region of low concentration in case of a system or mixture, and that may be in case of a liquid or gases, the molecular diffusion it takes place. Now this diffusion or this molecular diffusion it occurs when a substance diffuses through a layer of stagnant fluid, and it may be due to the concentration, temperature or pressure gradients also. So depending on the concentration, temperature or pressure gradients, we have seen that those diffusions are known as thermal diffusion or Knudsen diffusion, then force diffusion. So all these different kinds of diffusion also we have discussed earlier. Now in case of a gaseous mixture, what happens? The molecular diffusion it occurs due to the random motion of the molecules. Now this molecular diffusion it is actually also known as the eddy diffusion. So what was this eddy diffusion? Eddy is actually a high turbulent water mass. So in from this concept of the eddy we can get into the idea that in case of the eddy diffusion, the diffusion's nature, it will be in a turbulent. So that means what? When one of the diffusing fluid is in turbulent motion, then the eddy diffusion takes place. Now, in case of this eddy diffusion, this mass transfer, it is much more rapid compared to the molecular diffusion. So this is the concept of the diffusion mass transfer, and the difference between the molecular diffusion and eddy diffusion we have discussed just now. So we have seen that in case of the eddy diffusion, as the diffusing fluids is in turbulent motion, so the mass transfer is much more rapid compared to the molecular diffusion. So based on this concept of the diffusion, let us start this law, that is the main formula or the main law of this mass transfer, which is known as the Fick's law of diffusion. Now here you can see that the formula of the Fick's law, it is written here. So what is this Fick's law actually? And suppose the diagram which is given here, one chamber you can see, and inside this chamber there is one partition, and two different species are there, A and B. Now suppose consider there is a chamber which you can see in this diagram, in which two different gas species A and B, these are there inside this chamber, and these two different gas species, these are at the same temperature and pressure, and these are separated by the partition which you can see here, like the dashed line. This is the partition. Now the left compartment where the species A is there, the left compartment, it has a high concentration. So what is this high concentration? That means more molecules per unit volume. So this left compartment, it has a high concentration of gas A, and but in the right compartment is rich in gas B, which are actually represented by the dark circles. So in this left compartment we can see that these blank circles, these are the representation of the species A. Now, that means the left compartment has high concentration of the species A, but in the right compartment it is having the high concentration of the species B, which is actually represented by these orange circles. These are the high concentration of the species B. Now when the partition wall, that is the dashed line, has represented the partition wall in between the species A and species B. Now when this partition wall is removed, then a driving potential comes into existence, which tends to equalize the concentration difference. Okay, so what happens when we withdraw this partition wall in between the species A and species B? In that case, there is an existence of driving potential. Now this driving potential, it tends to equalize the concentration difference in between these two different compartments, A and B. That is the left compartment and the right compartment. Now the mass transfer by diffusion will be in the direction of decreasing concentration, and subsequently there will be a net transport of species A to the right compartment and of species B to the left compartment. This is obvious because the left compartment, it is having the higher concentration of species A, so obviously this higher concentration of species A, it will try to shift to the right compartment where the concentration of species A it is lower. So in this similar manner, again the higher concentration of the species B from the right compartment, it will try to shift, or it will try to move to the left compartment where the concentration of species B it is lower. So that means the transfer of species A and species B it will occur. Now after sufficiently long period, what will happen? Some equilibrium condition it will prevail there. So that means what will happen when the equilibrium condition will prevail? That means the uniform concentrations of species A and species B, these will be achieved. And after that sufficient long period when the equilibrium condition it will prevail, that means the uniform concentration will be there within this chamber, then the mass diffusion it will ceases. So this is the concept of this mass diffusion within this chamber. So this is an example we have taken here. Inside a chamber we have considered one partition, and in the left and right compartments we have considered two different species which are having their higher concentration in each of the chamber. Now after withdrawing that partition, there will be the movement or the transfer of the mass for each and every species for its higher concentration to lower concentration, and after sufficiently long period there the equilibrium condition will prevail. That means there will be the uniform concentration of species A and B within this chamber, and then only the mass diffusion it ceases. Now it is observed through experiments that molecular diffusion is governed by the Fick's law. The representation of the Fick's law, it is actually Na equals to Ma by A. So this is equals to minus dAb into dCa by dx. So what are these notations? This Ma, this is actually the mass flow rate of species A by diffusion, which is kg per second. Then capital A, it is the area through which the mass is flowing. So the unit will be m square. Now what will be this Ma by A? So this is represented by Na. So this is the ratio of the mass flow rate divided by area for the species A. So that means it will be now the mass flux of species A. That means what? The amount of species A which is transferred per unit time and per unit area perpendicular to the direction of transfer. The unit will be kg second per meter square or kg mole per second meter square. Next, what is this DAB? It is the diffusion coefficient or mass diffusivity for binary mixture of species A and B. So this is the mass diffusion coefficient or the mass diffusivity, and the unit is meter square per second. So this unit meter square per second, so it is having the same unit like the kinematic viscosity nu, which we have studied in fluid mechanics. That kinematic viscosity, it was dynamic viscosity by density mu by rho. So it is having the same unit, that mass diffusivity and kinematic viscosity, these are having the same unit, which are meter square per second. Next notation, it is Ca. So this is the concentration or molecules per unit volume of species A, and the unit is kg per meter cube. Next, dCa by dx, so it is the concentration of gradient for species A. So this acts as the driving potential. The unit is kg per meter cube. Now this Fick's law, it is having the similar kind of representation like the Fourier's law of heat conduction, and there also we have seen that the representation was q equals to minus k dt dx. The Fourier's law of heat conduction, there one negative sign was there. So similarly in this Fick's law also there is one negative sign. So what is the significance of this negative sign? This negative sign indicates that diffusion takes place in the direction opposite to that of increasing concentration. So this is also similar to the concept of the physical significance for the negative sign of Fourier's law of heat conduction. There also, in case of the positive x direction, the temperature difference, it was negative. So in this similar manner, the negative sign in case of the Fick's law, it indicates that the diffusion takes place in the direction opposite to that of increasing concentration. Now in this similar manner, we can write the diffusion rate for species B. So it is NB, this is equals to MB by A, so it is minus dBA into dCB by dx. Now this diffusion coefficient DAB or dBA, it is dependent upon the temperature, pressure and nature of the components of the system. So this temperature, pressure and of the nature of the components of the system, these are responsible for the diffusion coefficient in this Fick's law. So this Fick's law of diffusion, it is analogous to the Fourier's law of heat conduction, which we studied earlier, that is Q equals to minus K A dt dx, and Newton's law of viscosity. So this Newton's law of viscosity, that is tau equals to mu du dy, that is shear stress is proportional to rate of shear strain. This tau is the shear stress, mu is the dynamic viscosity. So this Newton's law of viscosity also we have studied earlier while studying the fluid mechanics. So this Fick's law of diffusion, it is analogous to these two different laws which are related to conduction and viscosity respectively. So that which are actually the Fourier's law of heat conduction and Newton's law of viscosity. Now by comparison of the above equations, that is the Fourier's law and Newton's law, we are getting that the Fourier equation describes the transport of heat energy due to temperature gradient. The shear equation describes the transport of momentum due to velocity gradient. But the Fick's law describes the mass transport due to the concentration gradient. So this is the difference in between this Fourier's law, Newton's law and the Fick's law. So what is this? The Fourier's law, it is the transport of heat energy due to the temperature gradient, which is related to the conduction. Then the Newton's law of viscosity is the shear equation describing the transport of momentum due to the velocity gradient in between the two different fluid layers. While the Fick's law, it describes the mass transport due to the concentration gradient. Now, this diffusion coefficient that we have seen earlier, how to find the dimension for this diffusion coefficient. The unit we have seen that it is meter square per second, which is similar to the kinematic viscosity. Now how to find the dimension for this diffusion coefficient? So from the formula, capital D equals to minus n by dc dx. So from the dimension analysis, we can find the unit for this diffusion coefficient. In case of this n, that is the mass flux, it is m by l square t, and in case of this dc dx, it is m by l cube and 1 by l. This says the concentration of molecule. It is kg per meter cube, so it is m by l cube, and dx, it is the distance or the length. So that means ultimately we are getting the dimensional analysis for this diffusion coefficient capital T, this is L square by T. So that means the unit will be meter square per second. So thus the unit of mass diffusion coefficient, these are identical to those of thermal diffusivity, that is alpha, and kinematic viscosity. And this diffusion coefficient is a transport property of the fluid. So the unit of this diffusion coefficient, this is identical to the kinematic viscosity nu and the thermal diffusivity alpha. So these three different terminology, these are having the same unit, that is meter square per second. Now by using the perfect gas equation, the Fick's law may be expressed in terms of partial pressure of species. So for species A, Pa equals to rho A Ra T. So using the relation that is G equals to Ma, we can write that rho A equals to Ca, this is equals to Pa Ma by Gt. Now substituting these values in the mass flux, you can write Na equals to Ma by A. So this is equals to minus dAb Ma by Gt into dPa by dx. Similarly, for species B, we can write the formula for the mass flux, that is Nb. Now these two equations, that is Na and Nb, these are valid only for isothermal diffusion. Now this mass diffusion coefficient, what will be its mathematical representation for gases or gas mixture by unit? Now by using the kinetic theory of gases, it is possible to predict the mass diffusion coefficient dAb for the binary mixture of two gases A and B. So its mathematical representation dAb, it is equals to T to the power 3 by 2 by P. This is equation number 13.23, and there is another representation, that is equation number 13.24. So here P is the total pressure in atmosphere, it is Pa plus Pb for the two different species, and capital T is the absolute temperature of the binary gas mixture. Va and Vp, these are the molecular volumes of constituent species at normal boiling points. Ma and Mb, these are the molecular weights of species A and B. For gas pairs of non-polar, non-reacting molecules, the diffusion coefficient can be written as equation number 13.27. These equations you need to remember to solve the numericals based on the concept of the Fick's law and the mass diffusion coefficient. Let us try to discuss the numerical based on this concept. Some data are given, so we need to calculate the diffusion coefficient for NH3 in air at 27 degrees centigrade temperature and atmospheric pressure. So what are the data given in here? NH3, that is the gas A, its molecular weight is given 17, and air, it is considered here as the gas B, its molecular weight is given 29. Now the molecular volume for the gas A, it is given 26.43 centimeter cube per gram mole, and the molecular volume for the gas B, it is given as 30.6 centimeter cube per gram mole. So for these two different species of the gas A and B, their molecular weights and molecular volumes are given. We need to calculate the diffusion coefficient for NH3 in air. So to calculate the diffusion coefficient for the binary gaseous mixture, we need to use this relation that is given as equation number 13.24. So this is the equation that we have discussed. It is equation number 13.24. It is the representation of the gas B, that is the mass diffusion coefficient for the binary mixture of two gases. In this numerical also two different gases are given, NH3 and air. So that's why we have used this relation of this diffusion coefficient. So in this formula we can see that the temperature it is given 27 degrees centigrade, which can be written as 300 Kelvin. Then PV it is given 30.6 molecular volume for species B, and VA it is given 26.43, and pressure is given 1 atmospheric pressure. So putting all these values in this new form relation, after several steps we will be able to calculate the value of the diffusion coefficient DAB, and that value will get as 0.183 centimeter square per second. So this is the procedure by which we have calculated the diffusion coefficient for NH3 in air. We need to remember the formula or the relation of the diffusion coefficient in case of the binary gaseous mixture, and there if you can remember that formula, then you can easily calculate its value in this numerical. Let us discuss the next numerical. From the following data, calculate the diffusion coefficient of carbon dioxide in air at a temperature of 25 degrees centigrade and atmospheric pressure. So what are the things given? CO2, that is gas A, that's sigma 3.996 Armstrong, and epsilon by K it is 190 Kelvin. For air, that is gas B, sigma it is given 3.167 Armstrong, and epsilon by K it is 97 Kelvin. The table given below may be used to estimate the collision integral ohm. So this table is given here. Sigma A for the carbon dioxide, it is gas A, it is given epsilon A by K, it is given 190 Kelvin. Ma is given 44, sigma B is given 3.167 angstrom, epsilon B by K it is given 97 Kelvin. Molecular weight of the species B it is given 29. Now we need to calculate the diffusion coefficient. So to calculate the diffusion coefficient, we need to use this formula that is written as equation number 13.27. So this is the formula. It is actually applicable for gas pairs of non-polar, non-reacting molecules. So we need to remember this formula where the ohm is the collision integral. So this formula we need to remember and we need to use in this numerical. Here sigma AB, it is sigma A plus sigma B divided by 2. So we can calculate the value of the sigma AB. So it is 3.5815 angstrom. After that epsilon AB by K. So this is actually root under epsilon A by K into epsilon B by K. This is the formula of epsilon AB by K. So putting all these values, we can calculate the epsilon AB by K. This is we are getting as 135.76 Kelvin. So epsilon AB by KT, so this is equals to 0.4556. So that means KT by epsilon AB, this is 2.195. Now corresponding to this value, KT by epsilon AB 2.195, the collision integral sigma, sorry, collision integral ohm, this is equals to this value that we have got from here. from this relation, that is sigma AB and epsilon AB, we need to use here in this numerical. Now in this way we need to calculate the collision integral of Ohm, that is 1.0418. Now substituting all these values, if we put all these various values in the above equation, that is equation number 13.27 for the diffusion coefficient, then we can calculate after several steps the value of diffusion coefficient, which we are getting is 0.171 centimeter square per second. So these are the procedure based on which we have calculated these two different numericals. So today actually we have discussed the Fick's law of diffusion, which is actually analogous to Fourier's law of heat conduction and Newton's law of viscosity. So giving an example, we have discussed the mass diffusion for Fick's law inside the chamber. After that, we have seen the mass diffusion coefficient formula for different cases, and based on those different formula we have discussed two different numericals. So this is the end for this lecture.